Inner transition elements F block. The F block consists of two series lanthanoids, the 14 element following lanthanum, and actinoids, the 14 element following actinium. Because lanthanum closely resembles the lanthanoids, it is usually included in any discussion of the lanthanoids, for which the general symbol Ln is often used. Similarly, a discussion of the actinoids includes actinium besides the 14 elements constituting the series. The lanthanoids resemble one another more closely than do the members of ordinary transition elements in any series. They have only one stable oxidation state, and their chemistry provides an excellent opportunity to examine the effect of small changes in size and nuclear charge along a series of otherwise similar elements. The chemistry of the actinoids is, on the other hand, much more complicated. The complication arises partly owing to the occurrence of a wide range of oxidation states in these elements, and partly because their radioactivity creates special problems in their studies. The two series will be considered separately here. Lanthanoids. The name symbols electronic configuration of atomic and some ionic states, and atomic and ionic radii of lanthanum and lanthanoids, for which the general symbol Ln is used, are given in table 4.9. So here the first is the electronic configuration. So it may be noted that the atoms of these elements have electronic configuration with 6s2 common, but with variable occupancy of 4f level. However, the electronic configurations of all the tri-positive ions, the most stable oxidation states of all the lanthanoids, are of the form 4f and n is equal to 1 to 14 with increasing atomic number. Atomic and ionic size. The overall decrease in the atomic and ionic radii from lanthanum to lutetium lanthanoid contraction is a unique feature in the chemistry of the lanthanoids. So it has far-reaching consequences in the chemistry of the third transition series of the element. The decrease in atomic radii derived from the structures of the metals is not quite regular as it is regular in M3 positive ion. This contraction is, of course, similar to that observed in an ordinary transition series, and is attributed to the same cause, the imperfect shielding of one electron by another in the same subshell. However, the shielding of one 4f electron by another is less than one d electron by another with the increase in the nuclear charge along the series. There is fairly regular decrease in the sizes with increasing atomic number. So here we see it's very gradual for 3+ oxidation state. The cumulative effect of the contraction of the lanthanoid series, known as lanthanoid contraction, causes the radii of the members of the third transition series to be very similar to those of the corresponding members of the second series. The almost identical radii of zirconium 160 picometer and hafnium 159 picometer, a consequence of lanthanoid contraction, accounts for their occurrence together in nature and for the difficulty faced in their separation. Oxidation states of the lanthanoids. So in the lanthanoids, lanthanum 2 to lanthanum 3 compounds are predominant species. However, Occasionally +2 and +4 ions in solution or in solid compounds are also obtained. This irregularity as in ionization enthalpies arises mainly from the extra stability of empty half-filled or filled F subshell. Thus, the formation of cerium 4 is favored by its noble gas configuration, but it is a strong oxidant reverting to the common +3 state. The E value for cerium 4 positive to 3 positive is +1 for which suggests that it can oxidize water. However, the reaction rate is very slow and hence cerium 4 is a good analytical reagent. Here ND, TV and DY also exhibit +4 state but only in oxides. MO2 EU2 positive is formed by losing the 2 S electrons in F7 configuration. F7 configuration accounts for the formation of this ion. However, U2 positive is a strong reducing agent changing to the common +3 state. Similarly, yttrium V2 positive which has F14 configuration is a reductant. TeV14 has half-filled F orbital and is an oxidant. The behavior of samarium is very much like europium, exhibiting both +2 and +3 oxidation state. So here we see lanthanum, it's F6D1, 5D1, 6S2. So lanthanum 2 positive is 5D1 and 4F0. Cerium, it's 4F1, 5D1, 6S2, 4F2. And with lanthanum 3, 4F1. Praseodymium, it's for lanthanum 3 positive, 4F2. Neodymium with 4F3 for lanthanum 3 positive. Promethium 4F4, samarium 4F5, europium 6, gadolinium 4F7, terbium 4F8, dysprosium 4F9, holmium 4F10, erbium 4F, thulium 4F12, yttrium 13, lutetium 4F14. And you see for lanthanum 3 positive is the variation, gradual degradation in the radius 106, 107, 103, 101, 99, 98, 96, 95, 94, 92, 91, 89, 88, 87, 86. So very gradual decrease, irregular gradual decrease in the ionic radii for lanthanum 3 positive.